Okay, to lead our final session of today, which is looking to space for answers on Earth, it is my pleasure to introduce Dr. Izabela Rottmann, who's the manager of RadioNet, the European Radio Astronomy Consortium. She advances European radio astronomy through leadership in various EC projects and international collaborations. She's the scientific manager at the Max Planck Institute for Radio Astronomy in Germany, and she plays the piano and accordion. Will you please welcome Dr. Izabela Rottmann.
Thank you, Chris. I will not play piano today, but I will take my 5 minutes extra. So we will stay for 45 minutes with you. The idea of looking to space for answer here on Earth is far from new, so disappointing maybe for you, but in fact it stretches back thousands of years. Ancient civilization gazed at the stars to navigate their ships, mark the seasons, and even seek meaning on their existence. While the questions have grown more sophisticated with the evolution of human technology, the answers we seek have become more complex and profound. So yes, the subject that we have today is not new, but is highly topical. My name is Izabela Rottmann, and it is my pleasure to moderate the session alongside the group of distinguished speakers that I will now invite you to enter the stage. Together, we aim to explore how the latest advancements in space observations are pushing the boundaries of knowledge and reshaping our understanding of the universe and of ourselves. This session will present cutting-edge development in space and ground telescopes and addresses the challenges we face in harnessing these remarkable tools. We also explore the transformative impacts of this technology on science, industry, and society. So to the beginning, each of the speakers will introduce, so it will be kind of like crash course for you on the infrastructures, which are really high technology development devices, let's say like this. And afterwards, we will follow with a panel discussion on the most burning topics which we found in the field. So we hope to leave you with many thought-provocative questions to be answered, if not at the end of the session, definitely over the dinner. So don't hesitate to come with a glass of wine to our speakers. They will be very happy. So now it is my pleasure to introduce the speakers that we have, and it will be in the order that they will present. First, Professor Ziming Cai, Innovation Academy for Microsatellites, Chinese Academy of Sciences, leading the Einstein probe. Dr. Fabio Bianco Marchet, Deputy Program Manager and Program Engineering of the European Extremely Large Telescope. Professor Elisabetta Barberio, Director of the Arc Center of Excellence for Dark Matter Particle Physics in Victoria, in Australia. And Professor Phil Diamond, Director General of the Square Kilometre Array Observatory, that we start with this today and we will finish. So, Ziming, the floor is yours.
Should bring my microphone?
No, just go.
Okay.
The slides should be shown.
Any slides here? Okay.
Yes.
Hello, everyone. This is Ziming Cai. I'm from Chinese Academic Science. This is a Orion invisible light. It is quiet and peaceful in the visible light, but actually it filled with various violent explosions and changes in the X-ray sky, which is invisible to human eye, as you can see. Is completely different with the visible sky. It contains important astronomical targets such as supermassive black holes, strong magnetic field, celestial bodies, and hot interstellar gas. To explore the To explore the X-ray universe, CAS built an Einstein probe called EP to search for key answers like how common are black holes and how do they swallow the stellar. And in collaboration with ESA and MPE. Two state of the instrument offers EP unprecedented sensitivity and panoramic view of the cosmos. Wide field X-ray telescope, so-called WXT, has a huge field of view around 3,850 square degrees, very big FOV, and the energy band from 0.5 to 4 keV, resolution 5 argminutes. And the follow-up X-ray telescope called the FXT, classic Water 1 type, 1 square FOV and 24 arcseconds resolution. Very great instrument to conduct follow-up observation. This is a EP launch picture we captured, and that is a separation from the satellite and the launcher. And this figure shows various X-ray sources detected by EP so far. Different colors represent different types of sources, including stellar flares, white dwarfs, neutron stars, and supernova. And about 60 bright X-ray transits, over 3,000 faint transits found by EP, prompting large space and ground-based telescopes to conduct follow-up observation. The most distant transient EP has detected is a gamma-ray burst EP240315. It's very interesting because we can see at the gamma-ray band, it only lasts like 50 seconds. But in softer X-ray, it lasts more than 1,000 seconds. Found out that relativistic jets not only form earlier, but also persist longer following the collapse of the massive star into a black hole, challenging previous models based solely on the gamma-ray data. And the second one is a very interesting challenge because it does not match any previous observed objects. It may represent an entirely new class of transient source. This discovery is pivotal for broadening our understanding of the X-ray transient source population and the extreme physical process at the play in the universe. How does EP achieve such a large FOV and high sensitivity? Thanks to the lobster eye X-ray focusing technology, which proposed by Dr. Roger in 1979, lobster eye micropole optics, so-called MPO. It has a revolutionary performance, can focus X-ray photons in a spot 3 times better, which means at least 3 times more sensitivity. This is the MPO plate. It's very small, but it is very, very sophisticated. Each plate has millions of micropoles in it. These micropoles are extremely tiny, with 40 millimeter side length, and the roughness of the inner mirror wall is better than 1 nanometer in IMS. Very complex optics. To tap the EP's full potential, our satellite team designed a special survey pointing. 3 pointings in 1 orbit. 3 orbit observation could cover the whole night sky. And if a transient appears in WXT FOV, it will trigger satellite follow-up observation autonomously fast maneuver while sending the alert to the scientists. Rapid communication is extremely important for time domain astronomy. So we developed a module that could transmit via Chinese Beidou global navigation system. The interaction between EP and the ground science center is as simple as sending a mobile phone message. So that time delay is less than 30 seconds. EP provides sub-arc-second attitude measurement accuracy, as well as the thermoelastic deformation. The transient localization accuracy of the follow-up telescope is 2.3 arc-seconds. At the end, I'd like to close with a quote from Paul Nandra, director of MPE. Einstein probe is listening to the universe, while the world is listening to Einstein probe. I have confidence that the Einstein probe would be able to find more answers about our universe in space. Thank you.
Okay. Just a very short overview of my organization and of my project. So ESO and the Extremely Large Telescope. In a few slides. Okay, forget this one. That's supposed to be the last one. Okay, so ESO, ESO, it stands for European Southern Observatory. So it's an international intergovernmental organization established already 62 years ago, and with the purpose of promoting the astronomical observation in the southern hemisphere. So initially it had only 5 member states. Today we have 60 member states, and we have a strategic partnership with Australia. So we are cooperating in some specific projects, and we hope that soon they will become, let's say, full member of the organization. In addition, as it has been mentioned this morning, we have an extremely tight relationship with our, let's say, host country, Chile, because all our observatories so far have been erected in that place, for the reasons that have been mentioned this morning, because it's an almost ideal place for ground-based astronomical observations. So actually, ESO is building the ELT, which is a quite large project, as you will see, but we already have quite a number of facilities operating. The first one to come already in the 60s was last year with 3.6 and 4 meter class telescopes, plus other smaller ones. Our flagship is the Paranal Observatory, again, that's been mentioned this morning, which has 4 8.2 main mirror telescopes, the UT telescope plus other, let's say, minor facilities. ESO is also in the partnership of the Atacama Large Millimeter Sub-Millimeter Array, again installed in Chile in the northern part of the country. It's a radio telescope. And finally, ESO is also supporting the CTA, the Cherenkov Telescope Array, providing the location for the south arm of this system, and also some logistic support. Now, coming to the ELT, why do we need the ELT? The answer is very obvious. It's because we want to see in the sky deeper, let's say deeper in distance, but also means in time. So here you have a comparison between the images that have been acquired by the Hubble Space Telescope, by the VLT, so our flagship using the adaptive optics, and this is a simulation of what we expect to get with the ELT. You will see that the James Webb Telescope is not mentioned there because we do not have yet this image, but it will fall somewhere in between. Now, extremely large, how big? Well, just to give you an idea, it will fit inside the Coliseum. So just fit inside, it's quite big. A more modern comparison is here with the Ariane 6 launcher, so it's as tall as like this, as this gigantic missile. Now, a few numbers, I will not go into all the details, but the key one is the diameter of the primary mirror, which defines the sensitivity and the resolution of the instrument. And then we have something like 10,000 of, let's say, still mass, which is supposed to move, because all this telescope moves to track the objects, and needs to move accurately and very smoothly. So that's already quite a challenge. And then we have a lot of other stuff like very high quality glass fibers and the like. So in substance, what we expect is that because of this large size, this telescope will have 5 times the capabilities in terms of resolution of the VLT, and even 500 times faster exposure time, which means that it will be very efficient in producing scientific data. So just a couple of pictures. As you can imagine, it's like a traditional telescope beside the size. So there is an enclosure which is closed during the day to protect the optics from the sun, and it's open during the night. Inside there is a quite complex structure, but which has only one function, to keep in position the several optical elements. And again, I will not go into the details, but just to mention the two major ones. The M1, so the main mirror, it's a segmented mirror, so it's a mosaic of almost 800 hexagonal segments, and each one is actively kept into position and shape. So the shape and the position is continuously controlled in the range of, let's say, a few tenths of nanometers. So you can imagine this huge structure which needs to be accurate in terms of nanometers, so atomic scale, basically. And then the other key element of the telescope is the mirror M4, which is what we call the adaptive mirror. It implements the adaptive optics. So the function of this mirror, which is 2.4 meters in diameter, but it's really a thin shell of glass, less than 2 millimeters, is to compensate for the, let's say, the atmospheric perturbations, because otherwise, without this compensation, the whole telescope will not be that useful. You will just collect a huge amount of incoherent light. So in order to control this M4, the adaptive mirror, there are almost 6,000 tiny fingers, like actuators, that are controlling it and changing its shape like 5,000 times per second. So what are the major areas, technological areas that have been impacted by the development of the telescope? First of all, of course, building very large structures in a seismic area. Chile, as we said, is almost ideal in many respects, but unfortunately it's very seismic area. So all this big thing needs to survive quite strong earthquakes. Large silicon carbide elements. Now, silicon carbide is being used almost everywhere, but big pieces of silicon carbides are still extremely difficult to manufacture. It's a very strong material, hard and thermally stable, but difficult to manufacture. And actually, this is still the remaining big technological risk of all this project. We have not been able yet to produce the full mirror M5. As we said, high accuracy positioning and sensing. We are talking about devices that can position something with a resolution which is lower than 1 nanometer. So again, atomic scale for something which is huge. In terms of control, well, this system will include many thousands of sensors and actuators. All of them need to work together at the same time at quite high speed, and this is quite a challenge from the control point of view. Also, we are using quite energetic lasers in this adaptive loop. We need to project several laser beams. Here you see one, but there will be 6 in order to compensate for the atmospheric perturbations. And finally, obviously, the detectors, or the eyes of the system. So we're talking about CCDs, CMOS, and other detectors. Finally, the situation as it is today, well, actually, this was a couple of months ago, so it's coming. Physically, it exists. We expect that the erection of the dome and the main structure will be finished by 2026, and we expect to start observations in 2028, if everything goes well, because we have been through so many problems, starting from COVID, the war in Ukraine, and so on and so forth, that we are not that confident that the things will go well until the end. So that's it, a very short introduction. Of course, you can contact me. You can look at the ISO site web, or you can find us in the socials. And,
okay, so, well, I will look at the sky in a completely different, did it work? Yes. In a completely different side. Instead of going on a mountain, we go underground. So it's a different way of looking and doing astronomy. So what I will discuss a little bit, this Stoll Underground Physics Lab is the first underground lab in the Southern Hemisphere. And a little bit is different from the way we work, the way we access, and what's going on, and what you saw before, and you will see after me. I'm getting, maybe. So this is a picture of the sun. It was taken by Super Kamiokande in Japan, and has been taken underground, many meters underground, a few hundred meters underground, and is taken with neutrinos. So what happened and why we build this underground lab, because when we are on surface, we are bombarded by cosmic ray and by light and everything you use in astronomy, radio astronomy. But also we have dark matter, that is the majority of the matter in our galaxy and the universe, and neutrinos, also quite abundant. And it's very difficult to do any kind of astronomy of observation of them on Earth. So if we go enough underground, for example, 1 kilometer underground or more, none of the things that you use for astronomy comes, or cosmic ray comes down, only dark matter and neutrino reach the underground lab. That's why we are building this underground lab as deep as possible to do this kind of, to see dark matter, the particle dark matter, we know from astronomy should be there, and neutrino, and study neutrino. So this is what I'm discussing, is the Stoll Underground Lab. This facility is in Victoria, is 300 kilometers, a little bit more from Melbourne. It takes 3 hours to go. And is in Stoll. Stoll is a small city in nearby the Grampians. There are 6,000 people. You can see there the place. And it's been built, it's quite recent, a couple of years ago it's been open. And we had a big support by the community. The community is incredibly supportive. This facility is not only underground, it is in an active mine, in a gold mine, the Stoll gold mine. That Stoll is a gold mine, in the sense it's been gold since the beginning of the gold rush in Australia. You can see there the picture of the mine. It's quite a large area. And this is different from other mines that are typical of Australia. Australia is either open cut or what we call decline mine. As you mine, instead of having a shaft, they build a road. And so when you go down underground deep, for example, 1 kilometer, you have a tunnel that goes around the mine. This is the tunnel. One of the tunnel that goes down to the lab. To go to the lab, we need to do 9 kilometers of tunnel to go 1 kilometer underground. So we are at 1 kilometer and 25 meters underground on the Stoll gold mine. Own the mine, and we are renting, in a certain sense, the part. We have very good support of the mine. If you have this kind of infrastructure on the mine, there are other 2 underground labs that I know that are in the mine, so Snow Lab and Bulby. You need to have a very good relationship with the mine, because also most of the costs are borne by the mine. There is ventilation that need to be done. You need safety, so if something happened, they need to rescue. There is fiber optics for computers and so on, electricity and so on, everything the mine is providing. So this is the completion of the lab. It's not a big lab, as I say. It's done in August 22, but it took at least 1 year to commission the lab. So this is here. So this is a little bit the activity that are going on after 1 year. So you can see that we start bringing infrastructure down. So there are some muon detectors. They are to measure the handful of muon that reach underground, because still they reach underground, and they're preparing, and we are preparing what we call the castle for the next very dark matter experiment that I will show in a minute. And also there is the idea of having a cryogenic facility there to do study about quantum computing, but also on quantum system that is quite underground, is becoming quite popular. The experimental hall is not very big. It's 10 meters by 30. We are, when we speak about underground lab, we speak about overburden. So it depends on the density of the rock upon the depth. And we have an overburden of about almost 3 kilometers water equivalent. So this is the first detector that we are bringing down. It's the Sabre South detector. It's 4 meters a cube, the box will be 4 meters by 4 meters by 4 meters, so it's quite large, and we will need to bring down. It's quite complex. The core is this sodium iodide, this part that you see, this copper enclosure. There will be sodium iodide crystal to see dark matter, and all the rest, this white stuff will be full of liquid scintillator, and the idea is to decrease the noise, because not only you're underground, this kind of experiment require also very low radioactivity, and even if you're underground, you have a large natural radioactivity. So you need to shield your detector, and then there is this big tank of liquid scintillator that will also decrease the noise that comes from the intrinsic radioactivity of the material the detector is done, even if we have very high screening of the material. So this is the other part that we are going to put down in 2025 is the dilution fridge, and this will enable this kind of research that we are doing, and underground again starts studying system like quantum system deep underground with very low radioactivity and is shielded by the cosmic ray. And the idea is that it's going around a little bit on the world that there is this new quantum technology that can be used for dark matter and neutrino experiment, and they're becoming more and more there. So this is more or less what I think I've done. No, this is the other thing I forgot, is about computing. Obviously, we are underground and we need to bring everything up. And so we use optical fiber that goes up for the 9 kilometers of the road, and they attach to the RadioNet and then they go in the normal system. So all of this is our DAQ, data acquisition, that we are, at the moment, we commissioned, and we can drive data. And this is quite, you can see it's quite complex. This is for the SEBRE experiment, but also for other room that we will bring the data outside the mine the moment they are going to Melbourne Uni, and then will be analyzed there. So everything different from other infrastructure. Most of the operation will be remote. We can have only access the infrastructure between 8 o'clock in the morning to 4 o'clock, because another time they do explosion, is a running mine. So yes, it's an interesting part of the research, and I think this is, I will do the engagement for question later. So that's where I am.
Well, thank you, and good afternoon. Just want to give you a few slides to introduce you to the SKA Observatory. I think those of you who saw the opening ceremony this morning will already be familiar with part of it, but just to put it all into context, we are an intergovernmental organization governed by a treaty. We now have 12 members. We're the new kid on the block. We've only been a treaty organization since January 2021. And so our membership is still growing rapidly. In fact, this year, we've had Canada, India, and just a month ago, Germany ratified the convention to become members. And we're expecting France and Sweden to do so early next year, with other countries coming. I show the map, not that I think you don't know where these countries are, but just to illustrate the unusual nature of our intergovernmental organization. We span north to global south, and equally from North America to East Asia. So it's a very unusual collaboration, and we'll come back to this in the discussion later on. What are we building? Well, it's a single observatory, but it operates 2 telescopes across 3 sites. So the headquarters is in the shadow of the 76-meter Lovell telescope, just outside of Manchester in the UK. And what we're building are the 2 radio telescopes, the animations for which you see there. So on the top is what we call SKA Mid, the mid-frequency array in South Africa, about 600 kilometers north of Cape Town. This will consist of 197 dishes, incorporating the 64 Meerkat dishes, which is a South African instrument that's already operating and producing science. And it will be spread across 150 kilometers. And then SKA low, which you saw this morning in the live link. By the way, I was quite relieved that that live link worked. But then maybe I shouldn't be surprised. That site is probably the best connected site in Australia. It has a fiber connection of 10 terabits per second. So it's not something, we should have expected it just to work, and I was very, very pleased that it did. So I won't say anything more. You heard the explanation this morning. We expect to be fully operational around the end of the decade, but unlike the ELT, as Fabio was describing, we don't have to have the full facility complete before we can start early science. As George Heald and Emma and Karen explained this morning, we can do science with only part of the facility complete. So we expect early science to be starting in a couple of years from now. We'll transmit the data to a network of what we call SK regional data centers around the globe. So we are setting this up inspired by the system that CERN set up to analyze LHC data. But data volumes are so much larger than the LHC ever generated. In fact, than any science project has generated to date. When fully operational, we'll be producing 700 petabytes of data per year of science products. And so processing that is one of our significant challenges. The reason we're doing it, of course, is science, to study everything from the early universe, a few million years after the Big Bang, to the origin of life, and pretty much everything in between. Just very briefly to show you where we are. We're 3 years into our 8-year construction phase, and we're more or less matching the plan. The plan is in blue, where we are the other lines. And just to show you some pictures, so this is what's happening at the SKA mid site. The second from the left there is a picture from 2 days ago, which shows the 8 of our dishes, or parts of 8 dishes, have now been delivered from our colleagues in China. And you see on the left there the first full SKA mid dish nearing completion. And then you saw a lot of this this morning, so I won't describe it any further. So thank you very much, and back to Izabela.
Is it on? Yes? Okay. So now let's go through some questions that we discover as or decided that these are the questions that are burning. So for astronomers, definitely what we are really asking for and looking for is the quiet and dark skies. On the same side, the humanity is progressing, and there is a huge need for connectivity. And it, of course, mirrors on many satellites. So there are like 40 Starlink satellites per week that are launched. We heard today already about SK8 and their need for the quiet zone. So my question goes to Fabio. Could you please explain what exactly the satellite technologies poses on astronomy?
Well, yes, indeed. Actually, we have seen that the trend is that we are building infrastructures that are more complex, more sensitive, and actually more sensitive also to environmental conditions. So as we have seen this morning, SKA low, for instance, is installed in a very remote place, also very well connected. And ESO instruments are also built in Chile in the middle of Atacama Desert for the same reason. But well, we cannot stop, let's say, the development of the countries. For instance, as it has been mentioned this morning in Chile, they are thinking about, going for, let's say, hydrogen exploitation with big farms and so on. And clearly, in the case of Chile, for ISO at least, we have a very good relationship with the government. So it's really a cooperation. They fully understand our concerns, as it has been said. And so we have kind of control on that. We have much less control on what happens in the sky. And especially nowadays in which, let's say, profit companies, so private, not longer the, let's say, agencies, are populating the space with their own devices. This is becoming a threat for all of us. I mean, radio telescopes, of course, but also for the, let's say, visible telescope. We can see these, let's say, low-orbiting satellites in our cameras. So they are really disturbing the observations. And this has been mentioned this morning, the Vera Rubin telescope, which does not belong to ISO, but it's a survey telescope, and that one will be especially affected by this kind of, let's say, disturbances. They will capture those satellites, these, let's say, large swarms of satellites that are passing by. So there the question is, well, maybe seeing the problem from the other side. So we have here an expert of satellites. I will ask him what he thinks about possible mitigation. So is there any communication, any way that we can improve the awareness of the damage those satellites can do to our observatories?
This is such a confused and interesting topic. Actually, in my apartment, we built science satellite for scientists, but with because the low Earth constellation, communication constellation, grows rapidly recently, and I personally joined one of the mission as well. We are going to launch like 20,000 satellites in the next few years. But I think it is a tendency for the huge constellation. Yeah, that is the exactly configuration like for our constellation. I mean, it's a tendency because it provided the humanity the communication service, and the people need it. I mean, in great demand. Otherwise, you won't put the investment on the projects, in my opinion. But as we can see, it gets serious pollution problem for the scientists, especially ground-based telescopes. In my perspective, that we need to balance in the science and the technology, especially aerospace technology. The satellite service needed to lower the street light. It could use the material like black coated materials instead of a multi-layer thermal insultant components. Also, in our industry, I suggest that we add one light shielding component as well. Also, we can change the pointing and the shape of the satellite. But essentially, to deepen our understanding to the universe, I suggest that we can, because we cannot make these constellations disappear. It's a market demanding. I suggest that we can go beyond this communication constellation, go beyond them. We can build, because with the cost reduced by the launcher, and with the technology advance, we can build more satellite, spaceborne satellite, and we can launch them to further in a deep space, like a Lagrange point 2, like a JWST goes. In that place, we can have a clear vision of our universe, I suggest.
Thank you very much for the answer. So my conclusion, my understanding is that, well, of course, we are not against technological advancement. We all see the advantages of having these, let's say, constellations of satellites. But technically speaking, there are possibilities of limiting the damage. So we should point on that and, let's say, establish a communication with the, well, let's say, with the users of those systems, and trying to convince them to, let's say, to mitigate the consequences.
Sure, but I think the more important thing is that let the government set the regulations for the aerodynamic industry, limited the reflection and the stray light from the satellite. It is really important.
So there is a space for the space law. Good. Now I will try to change the topic and go to the public engagement. And so we know that exploring of the universe required advanced research, long-term investment, and the public trust. In the same time, the complexity of the infrastructures that we have, the technological level that they bring with, are sometimes not in the same level of the places where they are located. So it can lead to misunderstanding and skepticism, which may influence governmental priorities, I believe. So I have a question first to Izabela. How can we effectively engage diverse communities in understanding and supporting basic research despite its complexity?
Well, our experience with a community in regional Victoria, well, is Australia, so it's not that you need to think about. There is always a minimum level of education, and it's quite a wealthy community also. I think it's communication, really engaging from the beginning. From the beginning, even before we start building the lab, we spend a huge amount of time going there, speaking with the people, engaging the community, having town hall, giving public lecture. We also spend quite a bit of time and quite a bit of investment, including with the School of Education in Melbourne, to work with the high school and the school, because this is quite an important part. For example, since the community, since we built SAPOL, well, the idea of SAPOL was there. In the area, the number of students picking up STEM increased of 50%. And in this kind of community, having more people, more young people going to school or pick up career in STEM is quite important. So it's really showing them that there is a gain, and the gain may not be technological. It's really the gain on the heavy engaging the community, understanding what we do. Most of the time, they're really excited of what we're doing. So there is really an excitement to understand on fundamental research. They really like to listen. They really like to be part. They really, really spending a lot of time explaining all the phase of the project, where you are, what we know, what we don't know. There is a very, very big excitement in Victoria, at least I can see all over, especially in this area where normally are quite remote. The idea that STOL goes and get presented in international conference all over the world, and everybody knows that this place in the middle of regional Victoria is known. This is also give a lot of pride. So it's really explaining the way. Don't treat them as one-off. And for us also, we have a complication because our infrastructure is in a working mine. So we are the tenant, and so it's important for us to also not only have the community for the engagement of politics, but also for the engagement of the mine, because it's very important for them to have us. It's very important to show that they do something good for the community. So if the community see that we do good for them, is part of the fulfilling for the mine what they need to give back. But I think it's never give it for granted, and must be a continuous engagement at different level, from the school, from the community. There are events in the community, for example, sometimes they have some fair or some events. We always have our booth, and we explain what we're doing, giving us some merchandise, so we are part of the ecosystem there, and they expect us to be there.
So for you, it was kind of like communication first to get the better education, then education will give the better life, and so on. So there is a future. Perfect. Phil, you showed the map with all these countries involved. So the question will not go to ESO, because ESO is already organized, but you made a whole way to really go to the governments, to talk to them, to convince them to build this great telescope on the Earth. Can you give us a hint? How can we do this? What kind of culture problems we will have in the future, and what we should do to assure that there is a long-term investment in such a building of such infrastructures?
Well, thanks for the question, Isabella. Well, just to use the SKA as an example, it was not a straightforward decision to adopt the intergovernmental organization model that is governed by a treaty. In fact, the precursor organization to the observatory, confusingly with the same acronym, it was the SKA organization, not the SKA observatory, was actually a small not-for-profit company based in the UK. Now that served its purpose during the design phase for the telescopes and ultimately the observatory. But I think all of the members who are actually, it was just like a company board, were very clear that that was not the sort of structure that would take us forward for the many decades that we expect the SKA to exist. So we looked at a variety of solutions, continuing as we were, setting up as a foundation. We looked at the ERIC, which has been adopted in Europe, but because of the diversity of membership that we had, it didn't really fit. There are hybrid solutions which some organizations adopt, but we settled on a treaty organization. And I must admit, it was a bit daunting when we started down that road. It took several years under the leadership of the Italian Ministry of Foreign Affairs to negotiate the details of the treaty. But I think it in terms of longevity for an organization like ours, it was absolutely essential. It gives us that stability, the political engagement from the member states. It will ultimately give us the stability of funding that organizations like ESO and CERN and similar have. It also will help us deal with some of the normal issues that arise through international project and engagement. But interestingly, actually, referring back to the first discussion between the two colleagues on either side of me, being an intergovernmental organization under a treaty, we are able to sit at the International Telecommunications Union as we are sector members there. We are also now permanent observers at the United Nations Committee on the Peaceful Uses of Outer Space. And so it's extremely relevant in terms of controlling our ability to control and mitigate the interfering environment that will impact the SKA radio telescopes. We are talking to the various companies about technical mitigations, but it's a bit like the Wild West at the moment in low Earth orbit, with different companies launching hundreds, thousands of satellites. Starlink has 7,000 satellites in orbit right now, with the expectation of having 40,000 in the relatively near future. So the mitigations are there, they're possible. Space law is ultimately the answer, but getting new policies and regulations in place, well, it moves at the speed that glaciers move. It's a very slow process. But being a treaty organization means we're in the room and we're able to influence policy. I think also being an organization like that, we're able to talk more directly to governments than we would if we were just that small not-for-profit company that we started out as. I mean, why would a government listen to a small company based outside of Manchester? Whereas an IGO, we actually sit on their radars because their parliaments actually signed a treaty. So I really think it's worth the pain for an international collaboration to go down that road. We're quite happy to offer advice for a small fee, which could be a glass of wine later on this evening if required. So I'm not sure there's much more I could add.
Perfect. And I think I can add also that SKA is hosting also the IAU office for Dark and Quiet Sky. Extra made of it since, I think, 2 years. So now, shortly, a crash question on you, because we have to have elevator answer. From your perspective, what is the most impactful way that exploring space can help us tackle the challenges we face on Earth? Who wants to take first?
Well, just taking out from SKA and my experience at CERN, I'm a particle physicist, not an astronomer, is cooperation. I think all these governmental kind of project, seeing also what happened with CERN over the year, it just changed really the landscape of how people do research and also promote. As I say, also CERN seat at the observer at the United Nations, and I think also change really how the country interact with each other.
Well, indeed, I can only concur with that in the sense that, well, beside doing, let's say, basic sciences of physics, we are also, I would say, improving the relationships, really steering cooperation, and especially in this, I would say, historical period. I think this is quite relevant, and I think it's a responsibility of all of us to insist in that. Sometimes can be a bit frustrating, but we need to continue.
I think it is important to combine all the observabilities, like a visible light, X-ray light, and including the gravitational wave detection method to deepen our understanding for the universe. Thank you.
So I think the international collaboration is key, hence the theme of this this conference, and what you've seen with the organizations and countries contributing to these facilities. But we are, I think one of the great things is that together we're undertaking some fantastic, some of the great endeavors of the 21st century in the basic science that we are making possible for the user communities. But a key element, and I think you touched on it with the public engagement, is the need to ensure that what we do, what we innovate, and what we discover is also made available to the public, because after all, it is their taxpayer dollars or euros or pounds or whatever that actually pays for the research infrastructures that we build and operate.
Thank you very much. I think there is not enough wine probably today that you will forgive me if we will prolongate even longer to take the questions. So we will take the question over dinner. And let's thank our speakers. And I hope you get inspired.